Okay. So your graphic calculator is battery operated. Every so often the batteries run out and it'll say battery low, but you actually have quite a few hours left. But when it says batteries low, let me know and I'll replace the batteries for you. These are used all day by all our applied math classes. As I said, you absolutely don't need them for trigonometry, but the sooner you can get used to the graphing calculator, the better we feel. So that's why we're starting to use them in class. The on button's at the bottom here, you can see. And you might have to clear something out. If you've got something weird on your calculator, there's a couple of ways to clear it. You'll see at the very top, there's a second button. Anything printed in blue, you're gonna have to hit the second button first. So if you ever wanna just go back to a blank screen, just go second quit. There, right? If you see right above the word mode, it says quit in blue. Okay, but if you open your book, it says, it talks about the graphing calculator. This is very important. We'll be using the TI-84 you'll be using it in grade 11 and grade 12. Each classroom has a set of calculators and you'll be assigned a number. This is a really important thing. It's important for you actually, not really anyone else, but it's important for you that you reset the calculator memory at the beginning of each class. Okay? This removes all other students' work because some students leave their work at the end of class. You'll probably just turn your calculator off, put it back, and forget about it. But it has all other students' work in, so it's got numbers programmed in that you don't need and that might cause you problems. So I'll show you how to do that in a moment. The classroom calculators are used throughout the day and have to stay in the classroom. Therefore, before you leave, you've got to put them back in the appropriate spot, or you may have to find yourself having to replace the calculator, right? Because we only have a limited number. Now, as I said, when you go home today, and if you still have some homework you want to work on, you can use your regular scientific calculator for trig. But in future units, you will need a graphing calculator. In the linear and quadratic units, you'll need one of these. So there's a couple of things. You can try and get your homework done in class, right? You can also go to the library and you can sign one out for just using in the library. The librarian, the lady behind the desk, has certain calculators for sign out. You can use them in the library, but you can also sign them out for 24 hours. So you can sign out overnight. So that's an option too. You just have to remember there's lots of applied math people, so it's first come, first serve. Yeah, right here. So we're going to get started in a moment just with a brief review to triangles. But before that, let's learn how to clear your calculator out. So you turn your calculator on. By the way, how do you turn your calculator off just to save battery power? Yeah, it's right above the on button. See, the words off are printed, so just go second off and it'll turn it on, or turn it off. Okay, this message always appears, so just clear it right there using the clear. If you see in blue, right above the plus sign, it says MEM. That stands for memory. Okay, that's what we want to clear. Every day when you come to class, you grab your calculator. So it's in blue, so I press the blue button, second MEM. And number 7 says reset. So there's a couple ways I can get to number 7. I can use my arrow keys, boom, 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 like that. Or I can just press 7, okay? Now it says that you want to clear your memory, and you want to clear everything. So number 1 is highlighted. So just press enter. Enter is like the equal sign, and it's also the enter sign, right? It says, resetting RAM erases all data. Do you want to replace all data? They're just being safe here, but yes, you do. You want to reset everything. You don't want anyone else's numbers. So it says RAM cleared. So perfect. Everything that would have been in the calculator is cleared. It's all set back to defaults. So once again, second MEM, number 7, and then number 2, number 2, or sorry, second MEM, number 7, number 1, number 2. Clear. Okay. So second mem, number 1, number 2, and you're just pressing enter, right? Enter, enter, enter. All right. Okay, so just a couple of quick things. We're just going to be using this very simply at the beginning. This keypad is just like a regular calculator, right? These are your main operators. Enter is equals. You'll see soon enough that we're going to be using sine, cos, and tan. This is a graphing calculator, means we'll actually be doing graphing. And all the graphing functions, which we're not going to use with trig, but all the graphing functions are up here. So when you want to play around, here's the y equals screen. You can enter any y equals statement, right? Like y plus 1. That's a linear statement. We haven't gotten there yet. And when you hit graph, it's going to graph the line for you, right? That's the real beauty of these guys. But we're a little ahead of the game there. We're just going to start talking about trig. So when you have extra time in class, you can start playing around. The more you play with this thing, the more you learn it, right? The more you know, which is why we're giving it to you now, like a little ahead of when you actually need it. So I'm just going to push that aside for a moment. And we're just going to talk about triangles. Triangles are very important in math and science. They're actually foundationally structurally important shapes that underlie many of our basic concepts and constructs in our world, right? So they're sort of the building block of many architectural features. The triangle itself has magical, mystical qualities as well. But for us right now, what we're concerned with is that a triangle is a three-sided figure, but we think of triangle in math class and science class as having 6 parts. 3 sides, 3 angles, right? Here's your typical triangle. It's got 3 sides, 3 angles. So it's an enclosed 3-sided shape. There are all different kinds of triangles. But your first factoid to remember, if you don't know this already, is the sum of 3 angles in any triangle is equal to 180 degrees. How many people knew that? Perfect. It doesn't matter how small or how big the triangle is. If we measured those triangles, you know those old-fashioned devices, those protractors? If you measured with a protractor, you'd find baby triangles, huge triangles. The angle measures themselves equal 180. Now, we're not going to be using anything in this class that is like anything that requires measuring tools like that. We're going to be using formulas for our to figure out the measures of angles and sides. So we won't do anything with actual protractors or not really rulers either. So this is your first thing. All 3 angles of a triangle equal 180. So that means that if we know 2 of the angles, we can easily find the third. The next thing we're going to get used to is seeing this symbol. Anyone know what that symbol is called?
Theta.
Theta, right? This is the theta symbol. And it's used in math to indicate an unknown angle measure. Unknown sides we usually call x's, and we've seen x's in our previous units. But for an angle measure, we use theta. It's a symbol out of the Greek alphabet. So that's what you'll see. So basically, you'll see theta symbols inside the triangles because they represent the measure of this angle. So the first job we have today is determine the size of theta in each of the triangles below. Round your answer to the nearest degree. Okay, so no decimals. So how am I going to figure out how big theta is?
180 subtract.
Yeah, that's probably the easiest way, right? I suppose you could have added these 2 up and then subtracted the total from 180. But it's just going to be 180 subtract 47 subtract 62. And if you're using your graphing calculator, one of the nice things, it's got this huge screen, so it holds more than one question, and you can see exactly what you typed in. So you can also check for errors, right? You know how sometimes you make errors just in typing in? So I have 71 degrees. What about the next triangle? I've got 50 degrees and a theta and another theta.
Are there 2 equal?
Yeah, if the symbols are the same, then they have to be equal measures. If I didn't want these 2 angles to be the same, then I would have to use a different letter out of the Greek alphabet. We usually use Greek alphabet letters for angles and English alphabet letters for sides. So and in fact, when you move up, you might actually see you might actually see different symbols for angles and sometimes in your math career. That's alpha, beta, that's theta. So if I wanted you to know that they were different angle measures, I would have to give you different symbols, okay? That would mean these all three are different. But in this case, it means the two thetas are the same. So then what's your answer? How big is each theta?
65 degrees.
How did you get that, Devin?
Mine is 50 from 180, which is 130, and then I divide it by 2.
Yeah, that would be about the only way I could think of doing this, right? You know that this 130 has to be split equally. So that means that each theta has to equal 65. And if you do a quick check, 65, 65, 50, that's going to equal out to be your 180. All right, so far so good. This 180 rule is very simplistic, but it's going to come in very handy in the days to come when we start talking about these triangles, okay? So super easy, find the sum of the unknown angle in each triangle below. Round answers to the nearest hundredth if you have to. That's kind of funny, I don't think you have to. These are all whole numbers. So everyone figure out the missing angle measure, I think. No, not right now. What does this box mean? It's a 90-degree, right? Okay? So remember the box means 90 degrees. So come up with your answers and we'll check up with each other in a moment. Okay, it looks like most people are just about finished. Inesa? Looks like most people are just about done. Not sure if the answers are in the back. Yeah, I think the answers are in the back, right? So you can check your work. So we've got what? Okay, any issues on this? We're just going to do a real quick talk about. Okay, everyone okay with this stuff? I mean, you're just subtracting, right? Agreed? All right, notice this triangle here. This theta equaled 45 degrees as well. Now we had a couple of these triangles here with the little box, a 90-degree angle. Does anyone know what a 90-degree triangle is called?
A right angle.
Yeah, it's a right angle triangle or a right triangle. So right triangle. They are going to be very important in about 5 minutes to us. They have really special properties. That right angle creates all sorts of interesting properties. This guy's kind of interesting too, right? His angles are equal. Now, it might not look like it from this picture. It should have been drawn a little better. But when we have a triangle, yeah, with equal sides, it can look like this. It doesn't have to be a right angle triangle. But if I do that, you know both sides are equal, correct? It's called an isosceles triangle, named after a Greek mathematician. Now, the interesting thing is, if two sides of a triangle are equal, they're partner angles. Each angle has a partner, the one right across from it. Their partner angles are also equal. Okay? What about this guy? So these guys were actually supposed to be equal. They don't look at what they should be. What about this guy if I did one of these?
Equilateral.
All sides equal, that's called an equilateral. Equilateral triangles are very interesting. If all sides are equal, and I don't know how long the sides are, I just drew a triangle, but any equilateral triangle has something very interesting about it. What else can you tell me about an equilateral triangle?
All angles are equal. The sum of all angles will equal 180.
So then what does each angle equal,
60.
right? You automatically know if you've got an equilateral triangle, each angle has to equal 60 degrees. Because if it follows the 180 rule, and it has to because it's a triangle, every angle measure has to be equal to 60 degrees. So that's kind of an interesting little side note. All right, so after we got used to the idea that all three angles of any triangle equal 180, now we're ready to explore on a much deeper level, and this will take us a couple of days, just the right angle triangles. And you've probably had a bit of experience with this in prior math classes. That's great, but they're so important, it's worthwhile to go over them again before we discuss the other types of triangles. So, a right angle triangle looks like this, right? Two of the sides equal, cross each other at a 90-degree angle. Now, only ever going to be one 90-degree angle in a triangle. I can't have two 90-degree angles in a triangle, can I? Because if I had a 90 and a 90, that gives me my 180. I wouldn't have any angle left over for the third angle. So that's interesting. The other two angles will be small angles, right? But the other two angles have to each themselves add up to be 90. So they'll be regarded as small. So another word that might pop out is the word perpendicular. Two lines, or two segments, in this case there's line segments because they're just parts of lines. When they meet at a perpendicular, it means they meet at a right angle, okay? So there's lots of words that kind of mean the same thing. Right angle is equal to a 90-degree angle. They mean the same thing. So you can see those terms used interchangeably. And perpendicular lines or line segments or sides. If you see the word perpendicular, you know that they meet at a 90-degree angle. So that's kind of a magic word. If you see that word perpendicular, you know you're meeting at a 90-degree. Okay, so we've talked about right angle triangles. Right angle triangles are so special. They're fundamental to building structures, right? Because walls have to be at perpendiculars. Most things grow at perpendiculars too, right? Like trees grow up, But buildings must be built at perpendicular, at right angles. Stairs, ramps, right? The structure that supports a wheelchair ramp has to be perpendicular. If it's not perpendicular, it's not going to last very long, right? It's going to start to crumble and implode. So 90-degree structures are very strong. Right angle triangle is, we have special vocabulary. The longest side of any right angle triangle is called the hypotenuse. Again, it's a Greek name. The two shorter sides, we just refer to them as sides or legs, right? At this point, they don't have special names. So how do I know what the hypotenuse is? It's always the longest side. And I hope that makes sense to you. We've already established that if there's a 90-degree angle, it's going to be the biggest angle, right? So that means it's got the biggest space between the two sides that make up the angle. Like these are the two sides that make up the 90-degree. This is going to be the biggest angle in the triangle. So these sides have to be the furthest apart. So that creates this side that's the longest, right? So the hypotenuse is always across from the right angle box. That's going to be hypotenuse. Visually, the hypotenuse has to be the longest side. So some triangles is very easy to see what the hypotenuse is just by looking at it, because you'll just look for the longest side. But some triangles are more uniform and it's more difficult to detect the longest side. So you just look for the box and just write the word hypotenuse. I usually shorten my hypotenuse to either capital H or HYP because it's such a long word. I want you to label the hypotenuse on the remaining 4 triangles. Okay, everyone good? Hypotenuse, everyone found the hypotenuse all right? Yeah? Okay, that's going to be important. So if you want to read a little more, Pythagoras, here's another Greek name. See, the Greeks get all the credit, but just remember everyone else was exploring and studying all these concepts just like the Greeks were. Mathematicians in India, Africa, all over Asia were doing the same thing, but these guys seem to get all the credit. He's credited with creating the discovery of special properties of a right angle triangle. You can see the right angle triangles embedded in here, right? And he did a whole bunch of work, and so did the other mathematicians, with like just counting, right? Counting sides and seeing the relationships. And then he basically came up with this, or this formula was synthesized after all this study, that they found that when you took the length of the 2 legs, right? You took the length of leg 1 and you squared it. You added the length of the second side and you squared it, and it is exactly equal to the length of the hypotenuse squared. So lots of teachers will teach it as a squared plus b squared is c squared. I prefer to say side squared plus side squared is hypotenuse squared. It makes more sense to me because they don't necessarily have to be labeled a, b's, and c's, right? So one side squared plus the other side squared equals the length of the hypotenuse squared. So that is the Pythagorean, or Pythagoras, however you pronounce it. That's the theorem. What does that let us do? Well, these right angle triangles are so important to building structures and things. They can help us determine missing lengths of construction projects, or not only that, there's other applications too. This is basically how they tracked, like how they started the study of astronomy, like how far away the stars and the sun were thousands of years ago before they had any technology. They used Pythagoras and right angle trigonometry to discover these things, right? And right angle trig is also how they constructed things like the pyramids. So it's fascinating, right? So what this allows us to do is, if we know two sides, or we can measure it, like we're capable of maybe measuring out two sides, that will help us find the third side of a triangle, or any structure arranged in this form. All right, so normally we call the length of the missing side x, right? The angle measures are thetas, those are the numbers inside the triangle. So to use Pythagoras, well, what will we do? Well, I know that one side is 6.5. So 6.5 squared plus 8.7 squared is going to be equal to x squared, right? Because this is the side, and this is another side, and this is the hypotenuse. So always make sure you know where the hypotenuse is. That's the most important guy, because it's the two sides squared that equals the hypotenuse squared. All right, so at this stage, I'm going to type that into my calculator. And your calculator nicely, I'll clear this out, it has a squared key, right? And it's nice, you can see everything you're typing in. 6.5 squared, and the squared key is right here above that kind of diagonal from the 7. Sorry, there's your 7 and there's your squared key. Plus 8.7 squared equals, okay, so I get 117.94 equals x squared. Now, the only problem with this theorem is it doesn't solve directly for x, right? It solves for x squared. So how am I going to figure out just what x is? I just want x. The square root, right? The square root, square rooting undoes squaring. I think I mentioned that once or twice in class, but these guys are inverse functions, right? These guys undo each other. Whatever I do to one side, I do to the other in math. Now, there's a couple of ways I can do my square rooting, but I think I'm just going to do it kind of the really straightforward way. Again, if you look in blue, right above the square, the x squared, what do you see above the x squared? The square root button. And that makes sense because they undo each other, right? They're opposites. So in blue, I'm just going to press the second, and then I get the nice square root sign. I'm just going to type in 117.94 and hit enter. And I'm going to round to 2 decimals because that's our default, 10.86. So the side is 10.86 centimeters long. Okay. So, example 2. Find the length of the missing side x. Okay, so here's x, right? I'm going to give you another example too. So side, hypotenuse. Agreed? Okay. Give that one a whirl. See if you can find the missing side.
I know how to type it up, like 6.5 squared plus 8.7 squared, and then that gives you an answer. What do you punch in after you hit equals? Yeah, well, I feel like 6.5
And then do you get the 117.95? 94?
Yeah.
Okay.
And then how do you incorporate that
So press your second button,
second function, x1?
second x squared,
Second function,
second x squared,
x squared. Okay, I got it.
and then punch in 117.94.
are you asking for 2 decimal places when it's only showing 1 on the other sides?
Because 2 is our go-to number in applied math. Just what the province has decided, actually, province of Manitoba. 2 decimals is what we do in applied. Unless you're told otherwise. Okay, what's your answer for x for example 2?
15.67.
Cliff got 15.67. Anyone agree with him?
Yeah.
Okay, that's the answer. Leah, did you get that? Tanis, did you get that? Okay. I'm going to assign you some questions, so I'll walk around and make sure everyone's comfortable with the calculator. I don't know, we definitely have to do an example 3, because this does not give you enough info to do the assignment. What about example 3? Find the length of x. Okay, label you know how I was always doing side, hypotenuse? I want you to label this guy as well. And tell me what the difference is. Why do I think we should do an example 3?
It's not the long side.
Mm-hmm. What's different about this one, Jordy?
It's not the longest side.
The x isn't the longest side this time. It's actually just a leg of the triangle, right? Side, side, hypotenuse. There's a little slight difference. Read. Now, it's still a right angle triangle. Pythagoras still works, but Pythagoras looks a little different when we set it up, right? What happens with this one? I get x squared plus 14.5 squared equals 21.7 squared. Agreed? This time I know the answer. I know the hypotenuse. I just need a side. So what did we learn at the very end of the last, we were talking about equations. When you're solving equations, you want to get the x by himself, right? You want to isolate him. So how would I get the x by itself? I have to get rid of this 14 point, right? I have to subtract him out. So that's the difference. The x squared is going to equal, the 14.5 gets removed from the left-hand side, and it also has to get subtracted from the right-hand side. Okay, so I have to figure out, this is, if you know the hypotenuse, it's not going to be an addition question, it's going to end up being a subtract question initially. Okay, so this time I got x squared equals 260.64. If you just remembered, if you remember to do the subtraction, then, the other steps are, can you guys turn your phones, the volume off, guys? The last step is the same, right? You're just square rooting. So my final answer is x equals 16.14 meters, I guess. Okay? So it's really important, for me it's really important to label, at least you should label the hypotenuse, right? And if the hypotenuse is x, it's very simple, just adding them up and square rooting. If the hypotenuse is a number and not the x, then you're going to have to do a subtraction. So I'm going to leave that, that'll be it for the notes, the formal notes. I'm going to assign page 5, Pythagorean theorem, and all you're doing is solving for the missing side. When you get back on Monday, because there's no classes tomorrow, when you get back Monday, we're going to start talking about the 3 right-angle trig ratios, the sine, the cos, and the tan. Okay? So I'm going to leave this with you. I see there's an assortment. This definitely is the hypotenuse. But this question here, that's the hypotenuse. So this is going to end up being a subtract question. Okay? All right, so take some time. Work on that